Hello everyone, my name is Rishabh and in this video we are going to see types of RNN. In the previous video, we have discussed what RNNs are and why they are needed for the sequential data. There we have seen what makes the RNN special, that is the memory retention feature of the RNN. That was really amazing. Now in this video, we are going to see the types of RNN. In the types of RNN, we are going to see two important things. Those are the architecture, that is how the information flows in the RNN, how the data flows in the RNN for each time step, for every type of RNN we are going to see. And the second, which is the real world application for each type of RNN. So I hope this video will be useful to you. Let's jump into it.
In this video, we are going to discuss three types of RNN. Those are many-to-one RNN, one-to-many RNN, and many-to-many RNN. For each of this type of RNN, we are going to discuss two things. Those are its architecture of all the three types of RNN, and then their applications. So that after this video, you will have a clarity that on which type of RNN, what kind of applications you can use and why. So let's start this video with this many-to-one RNN. In many-to-one RNN, as the name suggests, in input, we're going to have sequence of data. That is, in input, we're going to provide sequence of data, and in output, we are getting a single value. Input, we are providing a sequence of data, and in output, we are getting a single value. Let's understand this architecture. So for the architecture, we are taking three RNN cell. Those are the same RNN cell, but at the different timestamp. So at t equals to 1, we are providing an input x1. Now what will happen? Will I get the output? The answer is no, because this is many-to-one RNN. That means we must provide first all the input, then after the last input, we are going to get the output. Okay, so we are not getting the output in the timestamp t equals to 1. So what are we getting? Are we getting something after providing the input x1 after the t equals to 1? Yes, we're getting h1. Now what is this h1? This h1 is the hidden state which carries the information about the previous input x1. So this h1 carries the information about the previous input x1 and is going to be passed to the next timestamp t equals to 2 with another input x2. That is, this timestamp t equals to 2 are been provided with its current input and also the information about the previous input through h1. Now again, this x2 and h1 together will be making a hidden state h2, which we are going to pass to the next timestamp t equals to 3 with another input x3. Now this x3 is the last word in our sequence, which is the last timestamp. So in this, we are getting output O. This is how information flows in our many-to-one RNN. This is the architecture of many-to-one RNN. You can see why is it called many-to-one RNN, because we are providing a sequence of data and we are getting a single value. Now let's see the applications of many-to-one RNN. One of the popular application of this many-to-one RNN is sentiment analysis. Now what happens in sentiment analysis? In this, we're going to pass a sentence as an input to our RNN one by one, and that RNN will process that input and it will give us the output, the sentiment of the sentence. That is, if I say, for example, I'm passing an input which is Wi-Fi is down. Now here you can see I'm passing each word in each timestamp one by one. So RNN will process this input one by one. H1, H2 will be calculated, and then it will give us the output, which is the sentiment of the sentence. And you can see Wi-Fi is down is an input which sounds like a negative. So this RNN will give us the output as negative or 0. 0 means negative. This is how sentiment analysis works in many-to-one RNN. Another example, which is stock market prediction. Stock market prediction. Let's say now if I want the price of a particular stock tomorrow. Let's say if I want what will be the price of a particular stock tomorrow. So in output, I want price of a particular stock tomorrow. So this is the output that I want. So in input, what I'm going to pass is the prices of that particular stock today, price of the particular stock yesterday, price of the particular stock day before yesterday. That means what is happening here? We want a price of that particular stock tomorrow. So we are passing all the historical prices. So RNN will analyze all these historical prices and it will give us the price of that particular stock tomorrow. Obviously, this price will not be that much accurate, but it will be with some probability. This was about stock market prediction. So this was about many-to-one RNN, where we have discussed input is a sequence of data and output is a single value. Two applications that we have discussed are sentiment analysis and stock market prediction. Let's move on to our second type of RNN, which is one-to-many RNN. One-to-many RNN. Again, as the name suggests, in input, we are providing a single value. Input, we are providing a single value, and in output, we are getting sequence of value. Output, we are getting sequence of data. Okay, let's see how the architecture will look like. So these are the same RNNs which we have discussed in the many-to-one RNN. So at time step t equals to 1, let's say we are providing it with an input x1. Now here, will we get any output? The answer is yes. This time we are getting a output, which is say O1. And also a hidden state H1 will be calculated, which will carry the information about the previous input x1. And this H1 will be passed to the next time step, which is t equals to 2. Now here, we will be providing only one input because input is a single value. So we have already provided one input in our first timestamp. So after the first timestamp, we will not provide any input here. So the only information which will flow here will be hidden states. So at timestamp t equals to 2, we have provided with the h1 and we are getting an output which is O2. Again, h2 is calculated and we have passed that h2 at the next timestamp t equals to 3 and we are getting an output O3. This is how information flows in one-to-many RNN. This is the architecture of one-to-many RNN. Now you may wonder that on which kind of application this type of RNN is used. That is, we are providing only one input and we are getting multiple output. So this type of architecture is used in applications like number 1, text generation. In text generation, what happened? We provide a input, a text, a word. Say if I provide an input, say bird. Now that RNN will process this input and it will provide an output, a sentence that completes this word. So it may provide an output, say bird is flying, somewhat like that or something different. It will provide an output which will be a sentence completing this word. So this is text generation. One more application which we can consider for this type of RNN is image captioning. Now in image captioning, what happened? It is similar to some text generation only, but in input we are not providing a text, rather we are providing an image. Say image of a bird again. We are providing an image of a bird again which is flying. So we have provided an image of a bird which is flying as an input. So that RNN, what does RNN do? RNN will give us the caption of that image, that is what's happening in the image. It will give the caption for the image. So most likely it will give this same output which is bird is flying. So this was about image captioning. And also we have considered here only 3 timestamp. Let's say we have one more timestamp, say t equals to 4, then the output might be different. Then in that case, output will be, say, bird is flying high. Bird is flying high. So output might be different. It depends upon the number of timestamps. This was about image captioning. So in one-to-many RNN, we have discussed that takes a single value and it gives a sequence of data as an output. Applications we have discussed is text generation and image captioning. Now let's move on to our last type of RNN, which is many-to-many RNN. In many-to-many RNN, again, as the name suggests, input we are passing sequence of data, and in output we are getting sequence of data. Input we are providing sequence of data, output also we are getting sequence of data. That is the reason why it is also called as sequence to sequence RNN. Now this sequence to sequence RNN or many to many RNN can be broadly categorized into two types. Can be again categorized into two types. Those are equal length many to many RNN and unequal length many to many RNN. In equal length many to many RNN, what happens is the input sequence length is equals to the output sequence length. Okay. And in unequal length many to many RNN, just the opposite things will happen. Input sequence length will not be equals to the output sequence length. This was about equal length many to many RNN and unequal length many to many RNN. Let's discuss about the architecture and the applications of both of them. First, let's start with equal length many to many RNN. Equal length many to many RNN. Now for this, we're going to take the actual block diagram of an RNN cell. So these are the RNN cell at different timestamp t equals to 1, 2, 3. These are the same RNN cell. So previously we have discussed the RNN cell which looks something like this. So they are similar only. So in this type, these are the neurons, we know, and in each neuron there is activation function present. And by default for RNN it is 10H. So here it is 10H. And we know this might be input, this might be output, and this might be hidden state. So let's see how the information flows in this equal length many to many RNN. So at timestamp t equals to 1, we're going to provide an input x1. It's an equal length many to many RNN. That means how much input we are going to provide, that many output we are going to get. So at input, we're going to provide say x1. So at output, we're going to get o1 and a hidden state h1. At timestamp t equals to 2, we're going to provide an input x2. And we know x2 and h1 will together make us an output o2 and hidden state h2. Again, at timestamp t equals to 3, we're going to provide x3 and we are going to get o3 and h3. So you can see we are providing 3 input and we are getting 3 output. That is the reason why it is called as equal length many to many RNN. You might be wondering that what is this then? Just to maintain the consistency, we will take this as a 0 hidden state, that is 0 vector. Now let's understand this equal length many to many RNN with the help of an example. So say if I take an example of part of speech tagging. In part of speech tagging, what happens is if I provide an input, the cat sits, then for each input I'm going to get the part of speech of that input. Say here in x1 I have provided d, then the part of speech corresponding to d is determiner, then the output will be determiner. We are going to get the output determiner. We are going to get the output determiner. And here it is cat. So for this cat, we're going to get the output as noun. And for sits, we're going to get the output as verb. So here you can see for each of the word provided as an input, the RNN has given us the part of speech of that particular word. So this was about part of speech tagging. Now let's discuss one of the popular example of this kind of architecture, which is named entity recognition. Now, what is named entity recognition? Named entity recognition is a type of sequence labeling task. It is the type of sequence labeling task where each word in a sequence is classified into predefined categories. Categories like, if in our sentence we have a name of a person, then it will classify it as PER, that means person. If we have an organization, then it will classify it as ORG. If say we have location in our input sentence, then the output which we are going to get is LOC. If we have a date in our input sentence, then the output will be DATE. For rest of the other word, it will give us the output as O, that means other. So this is how we will label each of this word of our input. So this is the named entity recognition. Let's take an example of this. Say example we are going to take is Barack Obama was born in Hawaii in 1961. So here, if I pass this as an input to our equal length many-to-many RNN one by one at each timestamp, then what I'm going to get as an output? I'm going to get output as the label for each of this word. Now, what kind of label I'm going to get? For Barack Obama, I'm going to get label as PER, that means person. For Hawaii, I'm going to get the label as LOC. For 1961, I'm going to get label as DATE as an output. And for rest of the other words, I'm going to get the label as O, that means other. So this is how named entity recognition work for equal length many-to-many RNN. That is, for each of this word, I'm getting a specific labels. So this was about named entity recognition task. So this was about equal length many-to-many RNN, where we've discussed that if you provide a sentence as an input, then that many number of output we're going to get. For the example, we have taken part of speech tagging and named entity recognition. Now let's move on to our second type of many-to-many RNN, which is unequal length many-to-many RNN. Now what happens in unequal length many-to-many RNN? Here the input sequence length is not equals to the output sequence length. Let's first discuss the architecture and then we'll move on to the application part. For the architecture, we have taken the RNN cell, which is the same RNN cell but at different timestamp. Okay, so let's say at t equals to 1, I'm going to pass input x1. Okay, let's first draw the architecture and then I'll explain you what's happening here. At t equals to 1, we are providing an input x1. h1 is calculated from the previous input, which has been passed to the next timestamp t equals to 2 with another input x2. h2 is calculated, which has been passed again to the next timestamp with another input x3. h3 is calculated, passed to the next timestamp with another input x4. Let's say we are taking 4 inputs. We are taking 4 inputs and h4 is calculated, passed to the next timestamp, and from here the output has been calculated. Output has been calculated. So from here we can see some observation here. The input sequence length is not equals to the output sequence length. One observation is this. Another observation is the entire input sequence length has been processed first and then the output is calculated. You may ask why. It is because to maintain the context of the output. Let's say the first output, which is y1, depends upon the last input of the sequence. Now for that, the output must be produced after the last input, which is x4. So output might be depend upon any of the input. So that is the reason why, to maintain the context, to generate the contextually correct output, we provide the input, all the input first, and then output has been calculated. One more thing, that at timestamp t equals to 5 and t equals to 6, where the output has been calculated, no input has been provided. So the information about the input comes from the hidden state, h4 and h5. That is the reason why we call that the hidden state carries the information about the previous timestamp. So this was about unequal length many-to-many RNN. This was about the architecture part. Let's discuss the applications. So applications, as we all know, famous applications are chatbots. So in chatbots like ChatGPT, Gemini, Cloud, Anthropic, so there what happens, we provide an input prompt and we get output response. So the input prompt might be of different length, and the output which we get, the response, might be of different length. So this is one of the simplest example of unequal length many-to-many RNN. Here you can see this part is also called as encoder, and this part is also called as decoder. Further, when we will see the encoder decoder architecture, we can say that the encoder decoder architecture derived from this unequal length many-to-many RNN. This was about unequal length many-to-many RNN, where the input sequence length is not equals to the output sequence length, and we have discussed the example about the chat bots.